Okay, hello physicists. Welcome to our January 22nd edition of physics. Today we are going to try to get through all of the material we need to finish our homework. Now the homework I would like to have on Monday. I will not count it late, however, if you hand it in by this coming Wednesday. I'm saying that because I realize we're going over some things today that we did not go over on Wednesday, so I want to give you enough time to complete the homework. So today we're going to use this constant acceleration model more fully and kind of get in the weeds with it. So there is another thing I want to bring your attention to, which is that we have a quiz on Canvas. This should happen every Friday. We'll have a quiz. And in honor of this, to drive it home, I will go over a couple of quiz types of questions. Remember, the quiz is open note, open book. So please try to do your best. I think that the quizzes are a good place to rack up points, not a place to lose points. So for instance, here's a question. In which one of the following situations does the object not undergo acceleration? Well, remember, acceleration is where you have a change in displacement over time. So, for instance, if we have a ball at the end of a string is whirled in a horizontal circle at a constant speed, remember, acceleration has to do with changes in velocity. So velocity has a directional component. So if you're changing direction, you are, in fact, accelerating. That is not it. Seeing a red light at a traffic light ahead, the driver of a minivan steps on the brake. As a result, the minivan slows from 15 meters per second before reaching the light. Now, that can't be it. It's changing speed. Speed is a part of velocity. A boulder starts from rest and rolls down a mountain. Well, it's starting not moving. It ends, and it is moving. So it changed its velocity. That can't be it. An elevator in a tall skyscraper moves upward at a constant speed, that I like, of 3 meters per second. That's got to be it. And then this one, a ball thrown upward from the surface of the earth slows to a temporary stop at a height of 4 meters and begins to fall back toward the ground. Okay, that cannot be it either. Okay, so acceleration is change in velocity, change in how your displacement per unit time is changing. Okay, I have learned that sometimes if you want to get a point across, you have to say it a couple times. So I will say it again. We have a quiz on Canvas today. Every Friday, in fact, you will have a quiz or a test in this course. So here's another one. A particle confined to move along a straight line is accelerated at a rate of 2 meters per second squared. 2 meters per second. Every second is how the speed is changing. Which one of the following statements accurately describes the motion of its particle? It travels 2 meters during each second. No, it moves more meters every second it goes on. The particle travels 2 meters only during the first second. No, in fact, the first second it won't even get 2 meters because it won't have been going 2 meters per second the entire time. The speed of the particle increases by 2 meters per second each second. Now that I like. That looks like the right answer. And the acceleration of the particle increases by 2 meters per second squared. No, the acceleration is 2 meters per second squared. It's not increasing. And the final speed of the particle will be proportional to the distance the particle covers. In fact, it's proportional. Final position. No, I think it's proportional to the square of that. Okay, so last one. By the way, did you know that we have a Friday quiz on Canvas today? Worth considering. Open note, open book, closed neighbor. All right, so let's, with one last quiz type question, let's get into the sort of thing we're going to be looking at today. This is one that actually uses our constant acceleration model. Remember, our constant acceleration model says that the rate in meters per second squared, that the speed is changing each second is not changing, but the velocity in meters per second could be changing if the acceleration is not zero. So that causes the position in meters to be changing with some term that depends on time squared and some term that depends on time. So it says an object moves horizontally with a constant acceleration at time t equals 0, x equals 0 meters. Okay, this is at time t equals 0, so in our model that is x naught. For which of the following combinations of initial velocity and acceleration will the object be at x equals minus 1.5 meters at the time of t equals 3 seconds? So what are all the things that are in our constant acceleration model? Where you start, where you end up, how fast you start, how fast you end up, and the acceleration, which in turns, which it's important to notice, is the same at the beginning as at the end. This is constant acceleration is the key part of this model. Okay, so it asks what initial velocity and acceleration. So we don't know this, we don't know that. We could once we actually could find our v with this information. Let's see. I will let you plug these in because basically it's a fact of going x minus x naught equals v naught times t plus 1/2 at squared. This is going to be minus 1.5, and you can plug in things. I think you'll find that this is the answer. That just comes from putting in a plus 1 into there times 3 and a minus 1 in there and 3 squared right there. Okay, now the question is, what is the story this is trying to tell? Well, in my velocity versus time, it's going to be that I begin going forward and I end by going backwards. So I start out with a positive velocity, but I end up behind where I started. And so that means that I must go something like this. Okay, and then my position versus time graph looks kind of like this, where I go forward for a bit, I turn around where my v, there's my v versus t, here's my x versus t. Where my v versus t is 0, that's where I turn around and I start going backwards, and then at the end of our story, at t equals 3 seconds, I have ended up behind where I started at a negative x position. Okay, so it really is useful to sort of narrate these stories to yourself so you don't just get lost in the abstraction of all these symbols. Now, today we are going to have some problems where you're not just missing one thing, you're missing two things that you would need to solve the problem. So this is our constant acceleration, these are our basic equations. But let's say that you had a problem where you were missing the time and you were missing the acceleration, something like that. Okay? That would be this case, where you were missing the acceleration and you wanted to figure out how much time. But you knew, for instance, how fast you started, how fast you ended, and you know how much distance you covered. Okay? You could always do that sort of problem because if you have two unknowns and two equations, that's you know how to solve that. That's regular old algebra. So for instance, in that case, you would go ahead and say, okay, I would like to find, so let's say we're missing A and T, and you want to find let's say you wanted to find A. Okay? Well, in that case, what you would do is you would solve this equation for t. You would go v minus v naught over A is t. And then you would substitute that in here and go x minus x naught equals v naught times v minus v naught over A, and then plus 1/2 A times t squared, which would be v minus v naught over A squared. And then you could clean that up just a little bit, and you would end up with, for instance, this equation right here. Now, you might ask yourself, okay, are you going to give me those equations on a test? And I think the answer is, sure, why not? I'll give you these equations on a test. I'll give you these equations on a test. I am not that concerned about the whole math issue. I just want us to understand the physics of what's going on here. These are all instances of the constantly accelerated motion. So if you solve those, and you can always rearrange your equations and get them to look a little bit different. And from a physics point of view, you haven't really changed much. So let's look at a physics problem that I gave you on your homework set. Here's one where we're given an electron with an initial velocity that is fast, 1.50 times 10 to the 5th meters per second. Now this is very fast. It's 150 times 10 to the third, so that's 150 kilometers per second. So that's incredibly fast. It's not quite as fast as the speed of light, though, because 10 to the 5th, if you know your speed of light, that is around 3 times 10 to the 8th. So this is less than 1,000th of the speed of light. Enters a region with a length of L equals 1 centimeter. So my x minus x naught equals 0.01 centimeters. Where it is constant, where it is electrically accelerated. It emerges with a final velocity of 5.70 times 10 to the 6th meters per second. Notice that there's a non-accelerating region where that electron is just going at its initial speed. It's just, we assume that it's continuing to go at 1.5 times 10 to the 5th meters per second until it enters this place where there's an electric field that gives it a kick. All right? And it's asking us, what is its acceleration? Well, you could always, so what am I missing? I am missing my time, and I'm missing my acceleration. But because I basically have two independent equations here, I can go ahead and solve for that. I don't need my t. So what's one way that you could do it? You could solve the second equation for t, plug that in for t there, plug that in for t here, and then go ahead and solve for a. On the other hand, you could use these expressions, v squared equals v naught squared plus 2a x minus x naught. And you could solve this equation for a, where they've already done the work for you in this one, and the question will go a little quicker. So I'm okay if you just start with this equation and solve for a using this. So if you don't like to remember extra things, I have to admit I myself only remember these, and then I would just work it out. But I will give you these on a test, so if you want to work it like that, that's all right. All right, now last time we talked about how if you just were given x as a function of t, you could go ahead and find your speed or your velocity as a from the slope of the graph. So if you take the slope dx dt, you could get the velocity, and that would give you the correct sign, because if it has a positive slope, it would be going forward. If it had a negative slope, you'd be going backwards. Then if you took the slope of that, and you could find the acceleration, because the acceleration is how the velocity is changing with respect to time. And so essentially the information of velocity and acceleration is also contained in the position graph. Now, we might sensibly ask ourselves, is it also true that the information for the position is contained in the acceleration graph? And the answer is almost, but not quite. Now, you might remember in calculus that whenever you did an integral, you always had a plus c. And there's a good reason for that. The reason being that, let's say we start with acceleration. If we want to go ahead and try to find our v, we would take the area under the graph. Okay? So this is a derivative. If we take an antiderivative, that's an integral. We could find our v, but we would not find our total v. We would just find how much it has changed. Acceleration is the change in velocity. So we would have to get to our full acceleration, we'd have to add in that plus c, that initial speed. So it would be the integral from whatever time we had at our beginning to our time at the end of our acceleration with respect to t. And then if we went up another level, we could take the area under that curve and get our x minus x naught. That's how much our position changed, would be the integral from initial time to final time of v dt. Okay, so if you want to go from position down to acceleration, you have all of the information you need. If you want to go from acceleration back up to position, you have to supply a little bit more information. You have to supply your initial velocity, and then you have to supply your initial position. However, these methods can be helpful in solving problems. So let's see a homework problem that you can do with this. It says figure 215a gives the acceleration of a volunteer's head and torso during a rear end collision. At maximum head acceleration, what is the speed of the head and the torso? Well, they haven't given you an initial velocity, so I think they want you to assume the initial velocity of the head is going to be essentially 0. But if you wanted to find the change in velocity, what you're going to do for the head, for instance, look, here it's 0, 0, 0, 0, 0. And then if you wanted to find the v, it would be you finding that area under the curve. Area, of course, is going to be 1/2 base times height for this triangle. Notice that they are giving you time in milliseconds, so you're going to have to make sure the acceleration is given in meters per second squared. That's good units. Milliseconds is bad units. You want to change that into seconds. Remember, there's 1,000 millisecond equals 1 second, so you can always multiply by 1 to change your units and have that work out for you. Same idea for the torso. The speed of your torso, you're going to have a triangle, so you're going to have 1/2 base times height plus a time when the acceleration is constant. and then an area here where you have a trapezoid. And so for this one, of course, it's just area equals base times height. And for that one, the area, you have two different heights, and you can just do base times 1/2 h1 plus h2. You're taking the average of the heights times the base. Okay, so that one's not too bad if you understand the graphical method. Let's look at another one. This one, I think, you could do this entirely with your equations, but it, I think, is a little bit easier to see if you draw a graph. It says an electric vehicle starts from rest and accelerates at a rate of 2 meters per second in a straight line until it reaches a speed of 20 meters per second. The vehicle then slows at a constant rate of 1 meter per second squared until it stops. Okay, so let's draw a velocity versus time graph for this. It goes at, it speeds up at 2 meters per second squared until it reaches a speed of 20 meters per second. Then it slows at a constant rate of 1 meter per second squared until it stops. Okay, so this is 2 meters per second is the slope. Sorry, 2 meters per second squared is the slope. The slope of the velocity versus time graph is the acceleration. And then it slows down, so the slope here has to be negative 1 meter per second squared. Okay, so here we have 2.0 meters per second squared. There we have negative 1.0 meters per second. Now, I can tell you the way I would do this problem. I would use this guy, and for part A, you have 2 times. So let's call this T1, and this is T2. You could go ahead and say that for the first case, your V minus V naught, which is 0, is going to be A times T1, or in other words, your acceleration for that first part is going to be your change in velocity over your change in time, and you know what the acceleration is, you know what the change in velocity is, so you could find this. And then you could do it again for your second part. You know what your change in velocity is, you know what your acceleration is. You could go ahead and find that. All right, then then to find how much time elapsed, you would just go ahead and find that delta T1 plus delta T2. Okay, so find this time and then find that time. And then part B asks, how far does the vehicle travel from start to stop? Well, again, you could use your equations and have one region where you find out your distance that you travel, and then have another one where you find out your distance that you travel. I might just as well, though, if I know this T1 and T2, I could go ahead and just find this area and find that area using 1/2 base times height, and find that first distance and then add it to the second distance. All right, so that would give me the total distance that I traveled. That's what I call using your mixed methods. You're using some equations, you're using some graphs. Use whatever is easiest. You know, you're a capable person. Now, if you wanted to just use the equations, that would not be wrong. And so you do you, do what is ever most convenient and seems slickest for you to get the right answer. Okay, here's a slightly trickier problem. This is one that I'm going to sort of outline, but I want you to spend a bit of time on your own trying it out. If you find this one to be hard, we can always do it during office hours on Monday. Okay, so let's take a look at it quickly. I put this on because they do a similar problem to this in your book. It's not exactly the same, but if what I say right now is not helpful, I would suggest looking at this problem in the chapter where they do a similar thing. Okay, so let's read about it. It says, a certain elevator cab has a total run of 190 meters and a maximum speed of 305 meters per minute. Okay, so that V max is going to be important. 305 meters per minute. Just keep in mind that you're going to have to convert that unit for it to work nicely with the rest. And it accelerates from rest and then back to rest at 1.22 meters per second squared. Okay, so here's the story. Here's my velocity versus time graph. You're going to have a region where your elevator is speeding up at 1.22 meters per second squared. That's the slope. Then it hits V max, the maximum speed, and it goes at that rate for a while until it gets close to the top, at which point it slows down, and at that point the acceleration is slowing down, so the slope is going to be minus 1.22 meters per second squared. Okay, so it asks, how far does the cab move while accelerating to full speed from rest? Well, in this case, I know what I would do. I would simply find out how much time it takes, okay, and then plug this in or find that area. Then you can find the time, then take 1/2 base times height, because you know what Vmax is, to find how far it went. And then it asks, how long does it take to make a nonstop 190 meter run, starting and ending at rest? Well, I think you can see that this area and that area are going to be the same. So this amount of time and that amount of time are going to be the same. So then you just have to find out how much time does it take in the middle. Well, you know that the whole area here, the area of this plus that, is going to give you the whole distance that you went. So that entire distance is going to be 190 meters. So this plus this plus this is going to give you 190 meters. So if you know what this is and you know what this is, you can subtract those off from 190 meters. That gives you the rest of your area. But you just want to find out what the time is right there. You know what the Vmax is. Okay, so you can go ahead and find out what that time is. Then you know what this time is, so you can take that time plus this time plus this time, and you're done. Okay, so I admit that's a little bit of an involved problem, but I don't think it's too hard. I encourage you to take a shot at it, and if you want to do it during office hours on Monday. That's why I'm not going to count your homework late if you need to have till Wednesday to get it done. So take a shot at it, see how it goes. All right, those are the only problems that we're going to do today. That should get you through the homework that is due on Monday, or kind of on Wednesday. I will post another homework set this afternoon for those of you who just really love it, you can start working ahead. Our first piece of physics, though, I think I should at least mention. Everything we've done so far is sort of notation, trying to understand what the relationship between acceleration, velocity, position is. I don't consider that to be physics. It doesn't really tell you anything about the outside world. For these to tell you something about the outside world, you have to attach the model to some phenomena. So here's a phenomena that we can attach it to. I'm going to claim that our model for motion under constant accelerations is in fact relevant for objects undergoing gravitational freefall. So what's happening here? I'm claiming that when this ball player throws that ball upwards at some speed, I could draw his velocity versus time graph, and the velocity would slow down, slow down, slow down, slow down, stop, and then start speeding up, going down, like so. And I'm going to claim that the acceleration in that is basically constant, and that the rate of that acceleration is, or the rate of that change in velocity is negative 9.8 meters per second squared. What does the minus come from? Just by that, it's going downward. Okay, it's pointing downward. That's the direction that the speed is changing. And famously, if you suck all of the air out of a room, it doesn't matter if you drop a feather or a bowling ball or an apple. They all fall at the same rate. There's a nice YouTube clip. Maybe I'll bring it in on Monday, but I encourage you to look it up, where they did this famous physics experiment on the moon, where one of the astronauts takes a feather, takes a hammer, and they drop them on the moon, and they both drop in lockstep. Okay, they go. Both hit the moon at the same time. So we're going to use this model a lot for one of the favorite early physics problems. Throw something up, see it drop down. All right, so that's next week. So what have our big ideas of today been? Well, first, we can use the equations of our constant acceleration model to solve problems where one of the key parameters is missing. In fact, if we have two things missing, we can solve our problem because we have two independent equations, our velocity equation and our position equation. And sometimes, as we went through today, if you can draw out a graph using a graphical method like finding slope or area can help you to think through the problem. And then finally, our first piece of physics in this class, objects free falling by gravity have a constant acceleration of 9.8 meters per second, pulling them downwards, and can be modeled with our known expressions for constantly accelerated motion. Okay, thank you for watching. As I said, quiz today, so good luck.